Hello, dear friend. Now you will listen to the answers to the questions that come to mind before going to bed. Please don't forget to subscribe to get the latest sleep facts right away. Lie back and enjoy listening. Why does cement harden? Cement is one of the most common building materials on Earth. We find it everywhere, in bridges, houses, roads, dams. From the outside, it looks like an ordinary gray powder, but what happens to it when mixed with water almost looks like a small miracle. A hard, stony structure gradually appears from the soft, plastic mass. Why is this happening? Cement is made mainly from limestone, clay, and mineral additives. These materials are crushed and heated in a huge rotary kiln to a temperature of about 1,450 degrees Celsius. At this temperature, ordinary limestone, consisting mainly of calcium carbonate, decomposes and reacts chemically with clay. As a result, clinker is formed, a granular material that is later ground into a gray powder, and a little gypsum is added to slow down the solidification reaction. Gypsum makes the process more manageable. Builders have time to distribute the mortar to the application site before it begins to harden. When cement is mixed with water, a chemical reaction called hydration begins. This word means connection with water. Hydration is not just drying out, as many people think. If the cement had just dried, it would have remained brittle and loose. Instead, the water literally reacts with the powder to form new substances. The main minerals of cement are calcium silicate and calcium aluminate. When their molecules meet with water molecules, the structure is rearranged. They combine to form precursors of small crystals and gels of calcium hydrosilicates, thin intertwining formations, similar to a spider web. This microscopic spider web gradually fills the space between the particles. There is more of it every hour. It grows into all the voids, binds and seals the material.
You can imagine this process as the tightening of many tiny threads. When the water reaches each particle of cement, additional crystals begin to form at this point. They grow and adhere to each other, crawling in all directions, until the fragile wet mass turns into a monolithic stone structure. Interestingly, cement needs water to harden. Not just a wet surface, but the chemical participation of water in the reaction. If the mortar dries too quickly, the reaction will stop. The cement will not have time to fully harden and will become brittle. Therefore, on construction sites, fresh concrete is sometimes watered or covered with a film to retain moisture. In complete darkness and underwater, cement also hardens, which makes it indispensable for the construction of bridges and piers. The cement hardening process takes a long time. For the first few hours, it becomes plastic and begins to keep its shape. It gains most of its strength in a few days, but it may take 28 days or more to fully harden. And even years later, slow structural changes continue inside the material. The cement seems to live its stone life, slowly strengthening. The cement itself is only a part of the future material. If it is mixed with sand and water, you will get a solution. If you add gravel, you get concrete, which is the main building material of modern cities. Concrete can be poured into molds, machines, formwork. It can be given any idea of the architect. When water triggers a hydration reaction, the shape is fixed forever. Thus, cement hardens not because it dries out, but because quiet chemical work takes place between its particles. Water does not disappear. It becomes part of new substances. The loose powder turns into stone due to a reaction that takes place at the level of tiny molecules. This is a quiet, slow process of transformation, where a solid structure is born from the chaos of the smallest particles. It's as if a city is built first inside every drop of water, and only then in the human world. How is a diamond processed? Diamond is one of the hardest natural materials on Earth. It is appreciated not only for its rarity, but also for the shine that appears after proper processing. However, it is surprising that in nature, a diamond often looks quite inconspicuous, opaque, like a piece of dull glass. All the splendor appears only thanks to the skill of the cutter. The process of turning a raw stone into a sparkling diamond is a combination of precise science, artistic taste, and patience. First, the diamond is found and mined. It is extracted from kimberlite pipes, ancient channels formed by hot magma millions of years ago. At the factory, every diamond found is sorted. Stones are classified according to several parameters: size, shape, presence of cracks, inclusions, and natural defects. Even a small scratch inside a stone can affect its value and processing methods. At this stage, powerful magnifiers, microscopes, and even CT scanners are used. Modern technologies can build a three-dimensional model of a diamond to determine how best to cut it. Diamond is an extremely hard material, but it is not equally strong in all directions. There are so-called cleavage planes inside the diamond, the directions in which it can be split. It's like the fibers in a tree. If you chop along the fibers, the tree will split more easily than across. Therefore, the diamond cutter examines its internal structure before touching the diamond with a tool. The best solution is not just to reduce the stone, but to make it reveal maximum brilliance and reflect light in the right way. The first stage of processing is called splitting or splitting. If the stone has natural weak areas, the master strikes them with a special tool. But laser cutting technology is more often used. A high-temperature beam gently cuts through the stone where it cannot be done manually. This separation allows you to get several smaller diamonds from one large one. The next stage is mold grinding or brooding. The stone is given a round shape, resembling a ball. Historically, this was done by rotating two diamonds against each other, because only a diamond can scratch a diamond. Today, machine tools and special diamond wheels are used for this purpose. The stone rotates at great speed, gradually losing excess protrusions. At this stage, the diamond is not sparkling yet. It is just taking shape. After shaping, the most important and subtle thing begins: cutting. Faceting is the art of creating planes called facets. These small surfaces should be positioned at such an angle that the light entering the stone reflects off the edges and returns to the outside, creating a characteristic flicker. The classic round cut has 57 facets. Each face is a small, mirrored area, and each one must be drawn perfectly. Otherwise, the stone will lose some of its luster. During cutting, the master works with microscopic precision. The diamond is fixed in a metal frame and brought to a rotating disc coated with diamond powder. There is no other method of precise processing. The cutter's workplace is filled with the quiet hum of the machine. Each touch of the disc removes a layer that is only a few micrometers thick. Sometimes, a master can work with one stone for weeks. After cutting, polishing begins. At this stage, the stone begins to shine. Polishing smooths the surfaces of the faces and makes them perfectly smooth. It is she who turns a diamond into a diamond, a stone that catches even a weak ray of light and responds with an explosion of inner brilliance. When the work is completed, the stone is sent for evaluation. Experts determine its value by 4 key parameters. The 4C: carat, the weight of the stone; cut, the quality of the cutter's work; clarity, the number and nature of inclusions; color, the fewer shades, the more valuable. What is beer? Beer is one of the most ancient drinks in the history of mankind. It was brewed thousands of years ago in ancient Egypt and Mesopotamia. It was written about in Sumerian tables, mentioned in the legends of Northern Europe. But behind the simple exterior lies a surprisingly complex process and subtle chemistry. To get a drink with a mild taste, aroma, and golden sheen, you need 4 main ingredients: water, malt, usually from barley, hops, and yeast. Everything else is a nuance of skill. It all starts with grain, most often with barley. The grain itself is not yet suitable for brewing. It is hard and contains starch that yeast cannot use. Therefore, the grain is germinated, turning it into malt. Germination triggers natural enzymes that begin to convert starch into sugars inside the grain. When the sprout appears, the process is stopped and the malt is dried. The influence of drying temperature is huge. The higher the temperature, the darker and more saturated the future drink will become. Light malt will make the beer soft and fresh. Dark malt will add caramel and chocolate notes. This is how stouts and porters are born. The dried malt is ground and mixed with hot water. This stage is called mashing. The water activates the enzymes remaining in the malt, and the starch is finally broken down into simple sugars. It turns out to be a thick, fragrant liquid, a sweet wort. There is no alcohol here yet, only the potential for its birth. Next, the wort is filtered and brought to a boil. At this point, hops are added to it. The green cones of the plant that give the beer its bitterness and flavor. Hops are a natural preservative. They protect beer from spoilage and give it its characteristic freshness. Different hop varieties give different flavors: citrus, coniferous, spicy, or floral. The skill of the brewer is to find a balance between the sweetness of malt and the bitterness of hops. After boiling, the wort is cooled. Now comes the moment when the yeast takes over the work. They are added to the cooled wort, and fermentation begins. Yeast feeds on sugars and converts them into alcohol and carbon dioxide. This is one of the most ancient biological processes used by humans. Fermentation proceeds quietly, without interference, as if the drink lives its own inner life. Yeast determines not only the strength, but also the taste. There are two main types of fermentation. Top fermentation. At a higher temperature, the yeast rises to the top. This is what ales do. Low fermentation. At low temperatures, the yeast settles to the bottom. This is how lagers do it. The same set of ingredients can give completely different results. It all depends on the yeast and temperature. After the main fermentation, the beer is left to mature. At this time, the taste becomes softer. The aromas become deeper. Sometimes beer is filtered, but some varieties are left unfiltered, and then it retains its light, natural turbidity and rich aroma. When maturation comes to an end, carbon dioxide remains in the drink, or is added on purpose. It makes beer effervescent, lively, and gives a characteristic feeling of freshness. The beer is then bottled, caned, or kegged. Some species continue to slowly change their taste already in the container, as if they are breathing. This is how a drink is born that combines nature and craftsmanship. Beer is unique in that it does not hide its origin. Each ingredient leaves its mark on it. Malt gives the body and color. Hops give the character and flavor. Yeast gives the soul. And water gives the base. Even the composition of the water affects the taste. Mecca makes beer soft. Hard water emphasizes the bitterness. What is a photocell? A photocell is a device that reacts to light. When the beam hits it, a tiny movement of electrons begins inside, and an electrical signal is generated. It seems like magic. Light turns into electricity. But there's simple physics behind it, and one of the most beautiful natural phenomena is the photoelectric effect. For the first time, the idea that light can knock electrons out of matter appeared at the end of the 19th century. Scientists have observed that if light is directed at a metal plate, it begins to conduct an electric current. but no one understood why this was happening. Albert Einstein gave the answer, and it was for explaining the photoelectric effect that he received the Nobel Prize. He proved that light consists not only of waves, but also of particles, photons. Each photon carries energy. If a photon hits an electron with sufficient force, it transfers energy to it, and the electron leaves the atom. Electrons are knocked out, which is a photoelectric effect. A photocell is a device that uses this property of light. Its base is a thin plate made of metal or semiconductor. When light falls on it, the electrons begin to move, forming a current. A photocell doesn't just measure light. It's capable of converting it into electrical energy. There are several basic types of solar cells. Photodiodes are small semiconductor devices. They change the conductivity depending on the light level. Photomultipliers are ultra-sensitive devices that can detect even a single photon. Selenium and silicon solar cells used to be used in light meters and today in solar panels. The most familiar example of a solar cell is a solar cell. Each of its cells is a small photocell. People look at the panel and see just a smooth, dark surface. But on a microscopic level, there are constant reactions. Photons of sunlight knock out electrons. The electrons are sent into an electrical circuit, and a current is generated. The sun literally feeds the city with electricity. Solar cells are used everywhere, and we use many of them without even thinking about it. For example, automatic doors in stores open thanks to photocells that respond to a light beam that is interrupted when someone approaches. Street lights turn on in the evening and off in the morning because the photocell determines the light level. In fire detectors, the photocell detects smoke by changing the passage of the light beam. Cameras, smartphones, and video systems use arrays made up of millions of miniature solar cells. Each of them captures a small area of the image. The photocell makes the world responsive. It allows devices to see the light. To feel the process a little deeper, imagine a thin silicon wafer. It consists of atoms, each of which holds its electrons at certain energy levels. The light falls on the plate. A photon, like a small package of energy, crashes into an electron. If the energy is high enough, the electron leaves its orbit and begins to move. It's about the same as if you gave a person the opportunity to open a door they were locked in. The electrons begin to move, and a current arises. A photocell is not a battery. It does not create energy out of nothing. It only converts light energy into electrical energy. It happens quietly, without noise, without fire and fuel. The light gives a current, and that's it. Surprisingly, the photocell is sensitive not only to visible light. It reacts to both infrared radiation, heat, and ultraviolet. This makes it valuable in the creation of night vision devices, satellite sensors, and medical analyzers. If you think about it, a photocell is a point of contact between light and electricity, two fundamental phenomena of nature. One thing is a wave and a particle at the same time. Another
is the flow of charges that animate the equipment. A photocell connects them, translating the language of light into the language of electricity. How is whiskey made? Whiskey is a drink that is born from grain, water, time, and patience. It seems simple, but behind its woody fragrance and golden color lies a slow process that combines nature, craft, and chemistry. To create whiskey, you need only 3 ingredients: water, malt, usually from barley, and yeast. But the main thing is not the ingredients, but how they are turned into a drink. The first stage is malting. Grain is taken, most often barley, soaked in water and left to germinate. Inside each grain, nature triggers a process. Enzymes convert starch into sugar. This happens in the same way as when a seed is preparing to become a new plant. For whiskey, the moment is important when the grain has accumulated enough enzymes, but has not yet begun to actively spend sugar on growth. Therefore, the sprout is stopped and the grain is dried. Drying is carried out in special furnaces, sometimes using peat, an ancient coal from marsh plants. It is the peat smoke that gives whiskey from the Scottish Islands its smoky flavour. The dried malt is ground and mixed with hot water. This stage is called mashing. The warm water activates the enzymes, and the remaining starch is converted into sugars. It turns out to be a sweet, thick liquid. Wort. It can almost be compared to liquid bread. There's no alcohol here yet. It's just a malt-flavored sugar solution. The wort is filtered, separating the liquids from the husk of the grain, and transferred to large vats for the next step. Now the yeast is connected to the work. They are added to the wort, and fermentation begins. Yeast converts sugar into alcohol and carbon dioxide. The process is similar to making beer or wine, but the goal here is not to drink, but to create alcohol that will become the basis of whiskey. Fermentation lasts for several days. The result is a drink with a strength of about 7 to 10%, something between beer and young wine. It is called bragga or wash. This is where whiskey distilling begins. Distillation is the heating of a brew in a copper cube. Alcohol boils at a lower temperature than water and turns into steam. The copper cube is not an accident. Copper cleanses alcohol vapors from excess compounds, softening the taste. As the vapors rise up the column of the cube, they cool down and become a liquid again, cleaner and stronger. For whiskey, the process is repeated twice, sometimes 3 times, to achieve the desired purity. After distillation, alcohol with a strength of about 70% appears. But this is not a drink yet, only its birth. The main magic starts later. Alcohol is poured into oak barrels. These barrels are the heart of whiskey. The tree doesn't just store the drink, it communicates with it. Alcohol breathes through the pores of oak, absorbs tannins, aromas, and is colored. The tree shrinks in winter and expands in summer. The drink
slowly penetrates into the fibers of the barrel and returns back, filled with hints of vanilla, caramel, spices, soft smoke, or dried fruits. Some barrels are new. Others have already been used for aging bourbon, sherry, or port wine. Each of them leaves its own mark, its own whisper of taste. That's why two whiskies from the same region can be so different. Each barrel has its own character. The exposure lasts at least 3 years, and this is only according to the law. In practice, many varieties rest in barrels for 10, 12, 18 years or longer. Every year, part of the drink evaporates. This is called the angel's share. The old whiskey warehouses smell of wood, time, and silence. Everything is subject to expectation there. When the whiskey reaches the required maturity, it is filtered, sometimes mixed with whiskey from other barrels of the same style. This is called blending. Other varieties are left single malt. They come from the same distillery, from the same malt, and do not mix with others. After that, the drink is diluted to a drinking strength, usually 40 to 46%, and bottled. How does ether work? Ether is one of the first substances that a person used as an analgesic during surgery. Today, it is almost not used in medicine, but its role in history is huge. Ether has given people the opportunity to perform surgical procedures without excruciating pain. However, the very phenomenon of how ether acts on the body and consciousness is amazing, and worth a look inside this process. Ether is a volatile, transparent liquid with a characteristic sweet odor. It quickly evaporates and easily enters the body through the lungs when a person inhales its vapors. Ether molecules pass from the lungs into the bloodstream and are distributed throughout the body, including the brain. After a few minutes, the ether begins to change the state of consciousness. To understand how it works, you need to remember that our brain is a huge network of electrical signals. Neurons communicate with each other through chemical and electrical impulses. Everything from a simple blink to complex thoughts, emotions, or pain is transmitted through this network. Pain is also not just a feeling in the body. This is a signal that goes through the nerves to the brain. There, the brain reads the signal and tells the person, "There is damage, you need to react." The ether interferes with this signal system. It does not turn off the brain completely. It only slows down and distorts the transmission of information. Ether molecules dissolve in the fatty membranes of nerve cells. Neurons stop transmitting electrical impulses as actively as before. It affects a wide variety of areas of the brain. At first, a person feels light, relaxed, and dizzy. You can imagine this as a gradual attenuation of noise inside the head. Networks of neurons are working less actively. A person loses his sense of time. His movements become uncertain. Then comes a phase similar to alcohol intoxication. There is courage, sometimes laughter or emotional emancipation. Ether affects the centers of self-control and inhibition.
When the concentration of ether in the blood increases, the effect becomes deeper. The centers responsible for consciousness and pain perception are slowing down. This is what delighted the surgeons for the first time. The patient stopped feeling the body as a source of pain. He could hear and feel touch, but the pain channel stopped working. This condition is called anesthesia, a temporary loss of sensitivity. During the deep action of the ether, a person loses consciousness. The brain still receives signals from the body, but does not process them. The neural network falls asleep, but the dream is unusual. No external signals reach the area of consciousness. This is not natural sleep or fainting, but an artificially created peace in which a person is protected from pain. At the same time, breathing and heartbeat continue to work. These processes are controlled by the most ancient structures of the brain, the brainstem and the medulla oblongata. Ether acts mainly on the cortex, the area of complex thinking and perception, and on the thalamus, which transmits sensory signals. When the thalamus is blocked, the signals simply do not reach the I, consciousness. But the silence is not absolute. Ether also affects the systems responsible for emotions and memories. Therefore, many people do not remember anything about what happened during its operation. However, ether has a downside. It irritates the respiratory tract, causes coughing, and can be dangerous in high concentrations. Its vapors are highly flammable, which is one of the reasons why it has stopped being used in operating rooms where there is a lot of electrical equipment and oxygen. Modern anesthesia is based on other, safer substances that can be controlled more precisely. Nevertheless, the ether effect has become a real breakthrough for humanity. Prior to his appearance, operations were performed without anesthesia. People were being held down so they wouldn't move in pain. The introduction of ether has changed everything. Surgery has become a science, not a last resort. What are detergents? Detergents are substances that help remove dirt from surfaces, skin, and fabrics. They surround us every day. Soap, shampoo, detergent, dish detergent, floor cleaner. All these are varieties of detergents. At first glance, it seems that they simply wash away dirt. But there is a subtle chemistry behind this, related to how water interacts with fats and dirt particles. The most important quality of detergent is that it allows water to penetrate where it cannot penetrate on its own. Water perfectly dissolves salts, sugar, and most substances that have an electrostatic charge. But she can't handle the fat. The reason is simple. Water molecules are polar, while fat molecules are non-polar. They don't want to mix, like two groups of people speaking different languages. The fat remains in the pan, on the hands or on the cloth, despite the liters of water. And that's where detergent comes into play. It is based on surfactants. Surfactants are molecules with a dual nature. Each surfactant molecule has two parts.
The hydrophilic part is the head that loves water. The hydrophobic part is the tail, which lacks fat and repels water. These molecules act as intermediaries between two incompatible worlds. When you apply detergent to dirty dishes or clothes, its hydrophobic tails cling to grease and dirt particles. At the same time, the hydrophilic heads are drawn to the water. As a result, surfactants surround the fat from the outside, forming micelles, microscopic balls. There is a droplet of fat inside the ball, and outside there is a layer that likes water and easily washes away pollution. You can imagine it as a chain of little helpers who grab the fat and bring it to where the water can already take it. In addition to removing fat, surfactants reduce the surface tension of water. Ordinary water pulls itself into drops and cannot always penetrate into the pores of the fabric or under the dirt. Detergents make water more fluid and allow it to spread over the surface, enveloping any irregularity. The types of detergents vary in composition and purpose. Soap is the oldest type of detergent. It is made from fats and alkali. When fats react with alkali, a salt of fatty acid is obtained. This is soap. It has a mild effect on the skin and dissolves fat well, but it does not work well in hard water. Washing powders and liquid products contain synthetic surfactants, enhancers, enzymes, and bleaches. Enzymes help break down protein and starch stains, such as blood or food residues. Bleaches restore freshness to fabrics. Dishwashing detergents are designed to effectively remove grease, even in cold water, and quickly wash off without leaving traces. Shampoos and shower gels contain mild surfactants and additives that protect the skin, create foam, and impart fragrance. Interestingly, foam is not an indicator of cleanliness. The foam is caused by the air trapped in the surfactant layer. We used to associate it with efficiency, but in fact, it's not the foam that cleans, but the surfactant's ability to form micelles. Modern detergents may also contain flavorings to create a pleasant smell, conditioning additives in shampoos and gels, alkaline or acidic solutions to fight limescale or rust, antiseptics to fight bacteria. But there is also an environmental side to the issue. Old varieties of surfactants decomposed poorly in nature and could accumulate in reservoirs, disrupting ecosystems. Today, biodegradable surfactants are increasingly being used, which decompose under the influence of air and bacteria. And yet, the fundamental idea remains unchanged. Detergent is a chemical bridge between water and fat. It does an invisible job. It breaks the bonds of pollutants, turns them into soluble particles, and allows the water to carry the dirt away. Detergents are the quiet magic of chemistry that works every day. When we wash our face, wash our clothes, or clean our house, this process turns chaos into order and dirt into cleanliness. How do colors come about? Color is not a property of objects, but the result of the interaction of light, an object, and our brain. We see the world in color only because there is light around us, a stream of electromagnetic waves of different lengths. To understand how color appears, we need to understand the path of light from the source to our consciousness. First, about the light itself. Light is electromagnetic radiation. It comes in different wavelengths. Our eyes are able to perceive only a small part of this spectrum, from about 380 to 750 nanometers. Within this range, each wavelength is perceived as a specific color. Short wavelengths, about 380 to 450 nanometers, violet and blue shades. Medium, 450 to 570 nanometers, green and yellow. The long ones, 570 to 750 nanometers, are orange and red. You can imagine it as a rainbow. When white sunlight passes through raindrops, it decomposes into its components. This is how the spectrum appears, a kind of analysis of light into colors. Now, let's look at how objects get color. The objects themselves do not contain color. They simply reflect some wavelengths and absorb others. Our eye perceives only reflected light. For example, a red object absorbs all wavelengths except for red ones. It reflects them. Green reflects green. Black absorbs almost all the light. White reflects almost the entire spectrum. That's why wearing black is hotter in summer. Dark fabric absorbs light and turns it into heat. Now, about the eyes themselves. The retina, located on the back wall of the eye, has two types of photosensitive cells. The sticks are sensitive to light, but they do not distinguish colors. Thanks to them, we can see at dusk. Cones are responsible for color perception. There are three types of them. Some are sensitive to the red part of the spectrum, others to green, and others to blue. When light falls on the cones, each of them sends a signal to the brain depending on how much it is activated. The brain mixes these signals and translates them into a feeling of a specific color. The principle is similar to setting up a TV. From the three primary colors, red, green, and blue, you can get millions of shades. If one of the types of cones does not work or does not work correctly, color blindness occurs, a violation of color perception. Now imagine the situation. We are looking at a red apple. White light falls on it, which contains the entire spectrum. The skin of an apple absorbs the green and blue parts of the spectrum, but reflects the red. Only the reflected wavelength gets into our eye. Then the cones send a signal to the brain, and the brain tells us, this is a red apple. There is another way of color appearance. Mixing of light. Additive mixing. If you combine the rays of different colors, they add up. Red plus green equals yellow. Red plus blue equals magenta. Green plus blue equals light blue. If we mix red, green, and blue together, we get white light again. This is the model used by smartphone monitors and screens. But there are colors that do not arise from the reflection of pigments. They are called structural colors. Butterflies, peacock feathers, and some beetles do not have color pigment. Their wings and scales have a microscopic surface that diffuses light like a prism. Color is formed due to the way light is refracted and reflected. For example, the surface of the wing shimmers blue and green without any dyes. The brain also plays an important role in color perception. It analyzes not only the wavelengths, but also the context. The same shade may appear brighter or darker next to different colors. This has been proven by a variety of optical illusions. Our brain strives not just to capture colors, but to interpret them in such a way as to make the picture of the world stable and understandable. Sometimes the brain even adds something that is not there. This is how the phenomenon of color constancy arises. Objects retain color when the lighting changes. The red cup remains red in the shade and in the sun, although the light reflected from it changes. What is music? Music is the art of organized sounds, but this definition is too dry to convey its essence. Music is the language of emotions, rhythm, and time, a way to convey feelings without words. It exists at the intersection of physics, biology, culture, and psychology. To understand what music is, you need to look into its structure and nature, how it appears, why it affects a person, and why it exists at all. Let's start with physics. Any sound is a vibration. When something vibrates, a string, vocal cords, a speaker, it makes the air molecules vibrate. These vibrations move in waves and reach our ears. Music appears when vibrations become organized. They form a rhythm, structure, and patterns. If the vibrations are chaotic, it's noise. If they have a certain frequency and pitch, it's sound. If the sounds are arranged in a system, it's music. Music consists of several fundamental elements: sound and pitch. Each sound has a frequency, the number of vibrations per second. The higher the frequency, the higher the note sounds. For example, the note la often vibrates at a frequency of 440 Hz. Harmony is a combination of sounds of different heights. Rhythm. This is the order of sounds in time. Beats, pauses, repeated accents. Rhythm is the heart of music. He makes it move. Rhythm is rooted in biology. The heart beats rhythmically. Breathing rhythmically. Steps rhythmically. The timbre. This is the color of the sound. A violin and a flute can play the same note, but they sound different because they have different timbres and different forms of vibration. Timbre is what makes the voice of a loved one recognizable among thousands of others. Dynamics. The volume and softness of the sound. Changing the dynamics creates tension and relaxation. Music is not only a set of elements, but also the art of order and surprise. If the sound is completely predictable, it's boring. If it's too chaotic, it turns into noise.
Music is between these extremes. It creates expectations and violates them. This explains why the melody remains in the memory. The brain likes to discover patterns. Now let's move on to perception. The ear converts air vibrations into electrical signals. These signals get into the brain, and then a miracle happens. Music activates not just one area of the brain, but many at once. Auditory cortex for analyzing sounds. Motor zones are why you want to tap your foot. Limbic system, the area of emotions. A reward system is one that responds to pleasant things. Music triggers the release of dopamine, the pleasure hormone. Especially in moments of unexpected transition, such as the climax of a song or the turn of a melody. Scientists call this auditory anticipation. It's like our brain is playing a game. It's trying to predict which sound will come next. If the expectation is justified, it's nice. If it is violated, it is even more interesting. Music has accompanied man since ancient times. The first instruments, flutes made from animal bones, date back 40,000 years ago. Music predated writing. Scientists believe that its role is to unite people. In prehistoric communities, it helped synchronize actions during common rituals, strengthened the bond within the group, and helped convey emotions. Surprisingly, music affects not only emotions, but also physiology. Slows down the pulse rate, regulates breathing, reduces stress levels, helps you sleep. Music is a universal language. People of different cultures may not understand words, but intonations and emotions are read in the same way. There are studies proving that even babies respond to music. They like lullabies because they have a predictable rhythm and soft dynamics. Sometimes music exists without sound. Composer John Cage wrote the piece 4:33 33 seconds, in which the musician sits on stage in silence. The bottom line is that music is not just sounds, but attention to sounds. Even the audience's breathing becomes a part of the piece. What is irrigation? Irrigation is a water management system by which a person provides plants with the necessary moisture. Unlike natural irrigation, where rainwater fields by itself, irrigation allows you to grow plants where there is not enough precipitation, or to regulate the amount of water at the right time. This practice has been around for thousands of years. The first irrigation systems appeared in ancient Egypt, Mesopotamia, and India, when people learned how to divert water from rivers and canals to fields. Thanks to this, agriculture appeared, and the opportunity to build civilizations independent of the randomness of the weather. Irrigation can be simple or complex. The easiest way is through ditches and furrows. Water flows through them, gradually saturating the soil. In history, such systems have made it possible to support life even in desert areas. For example, in Egypt, the Nile overflowed its banks every year, spilling over the fields. People built canals, dams, and reservoirs to collect water and distribute it evenly. This made it possible to harvest several crops per year, despite the variability of the climate. With the development of technology, more sophisticated methods have emerged. One of them is a sprinkler system.
where water is sprayed under pressure and falls evenly on plants. This simulates rain and is suitable for large fields. This method saves water and provides optimal moisture to plants. Another modern solution is drip irrigation, in which water is supplied slowly and precisely to the roots. This method is especially important in arid regions because it reduces evaporation and moisture loss. Irrigation affects not only the amount of water, but also the quality of the crop. Systematic watering allows plants to develop roots better, receive nutrients, and resist diseases. In hot climates, agriculture would be impossible without irrigation, and people would not be able to eat a varied and stable diet. However, irrigation also has its own problems. Excessive watering leads to salinization of the soil. Minerals from the water accumulate on the surface, making the land infertile. Improper water distribution can destroy canals, causing erosion, and alter natural ecosystems. It is important to plan irrigation so that it benefits, not harms. In the past, this was often ignored, and some ancient civilizations declined, precisely because of the destruction of land caused by the misuse of water. Irrigation is not just about agriculture. It is important for gardens, parks, lawns, and sports fields. Even small systems can create a microclimate, keep plants warm, and improve air quality through evaporation. From the point of view of engineering, the creation of an irrigation system is the science of resource allocation. It is necessary to take into account the relief, the speed of water flow, the needs of different plants, seasonal changes in precipitation and temperature. Pumps, reservoirs, pipelines, and automatic humidity sensors are often used for irrigation, which turn on water only when plants really need it. Irrigation is also an element of sustainable agriculture. In modern conditions, it helps to save water and get a stable harvest, despite climate change. The combination of traditional methods such as canals and furrows with high-tech systems makes it possible to grow food in the most difficult conditions. Irrigation is thus the art and science of water management. It allows a person to talk with nature, direct the flow of a river or rainwater, so that plants receive exactly as much as they need. From simple channels to automated drip systems, all this work makes agriculture possible in regions where plants simply would not survive without water control. Irrigation turns water into a tool that allows people to create life and provide food for entire societies. How is carbon-14 used to determine the age of objects? Carbon-14 is a radioactive isotope of carbon that helps scientists determine the age of organic objects. This method is known as radiocarbon dating or carbon-14 dating, and it has allowed us to reveal the age of ancient remains, works of art, historical ruins, and even the remains of ancient plants. The secret of this method is that it relies on the natural transformation of carbon atoms that occurs in the universe and in living organisms. Natural carbon consists of several isotopes. Most of it is carbon-12, a stable atom that does not change with time. Carbon-14 is formed in the upper atmosphere by cosmic rays. High-energy particles collide with nitrogen atoms, and one of them turns into carbon-14. This isotope is radioactive. Over time, it decays, turning back into nitrogen. The half-life of carbon-14 is about 5,730 years. This means that every 5,730 years, half of the original amount of carbon-14 disappears. Living organisms are constantly absorbing carbon from the environment. Plants take it from carbon dioxide in the air. Animals get it through food. Due to this, the entire living organism maintains a stable ratio of carbon-14 to ordinary carbon-12, the same as in the atmosphere. The process of life maintains balance. As long as the body breathes and eats, the carbon-14 level in it remains constant. When an organism dies, carbon metabolism stops. From this point on, the amount of carbon-14 begins to decrease because it decays. The amount of carbon-12 remains unchanged, as it is stable. By measuring the ratio of carbon-14 to carbon-12 in the remains, scientists can calculate how much time has passed since death. The less carbon-14 remains, the older the object. Special devices are used for measurement, such as radioactivity counters or accelerator mass spectrometers. They are able to detect even tiny traces of a radioactive isotope. Sometimes, researchers take microscopic samples of fabric, wood, or coal. A minimal amount of the substance is required for analysis. The results are checked several times to eliminate errors. The carbon-14 method is limited by certain limits. It is effective for objects up to 50 to 60,000 years old. Before that time, the amount of carbon-14 became too small to be accurately measured. In addition, the method only works with organic materials, bones, wood, tissues, and plant remains. A stone or metal cannot be directly determined using carbon-14, although sometimes organic residues next to them are examined. Radiocarbon dating has revolutionized archaeology. Thanks to it, it is possible to accurately determine the age of ancient settlements, mummified bodies, pottery, textiles, and even ancient ships. For example, using this method, scientists have determined the age of Tutankhamun's tomb, ancient human sites in Europe and North America, as well as historical artifacts from Egypt and Mesopotamia. However, the method requires caution. Excess carbon sources sometimes enter the atmosphere, for example, from volcanic activity or industrial production, which can change the natural carbon ratio. Calibration curves and additional verification methods are used to ensure accurate results. Using carbon-14 is not only a scientific tool, but also a window into the past. With its help, we can look into history thousands of years ago, understand when plants, animals, and people existed, assess the speed of development of civilizations, and even trace the migration
of ancient tribes. Radiocarbon dating connects physics and biology, chemistry and archaeology, helping us measure time that is long past and understand the context of human history and nature. The carbon-14 method reminds us that all living things are part of a continuous stream of time, and that even after death, the body continues to leave tiny traces of its existence that can tell us its story through the millennia. What is an autopsy? An autopsy, or autopsy, is a medical procedure by which specialists examine the body of a deceased person to determine the causes of death, assess the condition of organs and tissues, and identify possible illnesses or injuries. At first glance, this practice seems dark and frightening, but its role in medicine and society is enormous. Autopsy helps not only to establish the truth, but also protects the health of the living, allowing them to understand the nature of diseases and prevent epidemics. The autopsy procedure is performed by a pathologist. It begins with an external examination of the body. The specialist evaluates the general condition, records the skin color, the presence of injuries, wounds, bruises, signs of violence, or external signs of illness. These observations are recorded in the protocol and photographed for further analysis. An external examination is important because many signs, such as bluish skin or burns, can give clues about the nature of death. Then, proceed to the internal examination. Usually the body is placed on a special table and the organs are examined systematically. First, incisions are made on the chest and abdomen to open the chest and abdominal cavities. This allows you to study the heart, lungs, liver, kidneys, stomach and intestines. Each organ is assessed visually. Its color, consistency, the presence of tumors, hemorrhages, or inflammation. Tissue samples are sometimes taken for microscopic examination. This can identify infections, diseases of internal organs, or signs of chronic diseases that were not noticeable during life. The heart and blood vessels are especially carefully examined. Cardiac disorders are one of the most common causes of sudden death. The pathologist evaluates the thickness of the heart wall, the condition of the valves, the presence of blood clots or heart attacks. The lungs are checked for fluid, inflammation, or signs of suffocation. The liver and kidneys are looking for changes related to toxins or long-term illnesses. The gastrointestinal tract is also examined to find out if there has been poisoning or internal bleeding. An important part of the autopsy is the examination of the brain. It is carefully removed through the skull and fixed for a further examination. The brain shows traces of injuries, strokes, tumors, or degenerative changes. It is this stage that makes it possible to understand whether death was caused by the nervous system or a head injury. During the autopsy, biological samples are also taken for laboratory analysis. These are blood, urine, bile, and stomach contents. Modern methods include toxicology, genetic analysis, and microbial research. Sometimes the cause of death does not appear visually, but only at the molecular level. For example, poisoning, infections, or rare hereditary diseases. An autopsy has not only medical but also legal value. A forensic autopsy helps determine whether a person was killed, died of natural causes, or died in an accident. The pathologist records all the data in a report that can be used in court, in the investigation of crimes, or in insurance proceedings. Despite its importance, autopsies often provoke cultural and emotional resistance. Different countries and religions have strict rules about who can perform an autopsy and how to handle the body, and what procedures are allowed. The pathologist is obliged to act with respect to the deceased and his relatives. Modern medicine is increasingly using alternatives to traditional autopsy. For example, computed tomography or magnetic resonance imaging allows you to examine internal organs without incisions. However, a full autopsy remains the gold standard for accurately understanding the causes of death, especially when it comes to court cases or mysterious cases. Why do golf balls have holes? If you look closely at a golf ball, it seems that it is covered with small depressions or holes called dimples. At first glance, they may seem like a decorative element, but in fact, dimples play a key role in how the ball flies. Without them, the ball would fly much less accurately and much shorter. The history of their appearance, as well as the physics explaining their necessity, shows that golf is a game where even the smallest details are of great importance. Initially, golf balls were smooth. Early 18th century versions made of wood or packaged leather with feathers inside flew unpredictably. When the first rubber balls were created, they were also made smooth. The players noticed a curious effect. Balls on which the surface was accidentally uneven, due to cracks or puncture marks, flew further and more steadily. That's how the idea came up to make the surface specially uneven. Dimples affect the aerodynamics of the ball. Any object moving through the air encounters resistance. For a smooth ball, the airflow forms a strong swirling wake at the back, creating a lot of resistance. It's like water pulling a smooth stone along with it. The air contracts and lags behind, forming turbulence that slows down movement. For a golfer, this means that the ball loses speed faster and flies less. When dimples appear on the surface, they change the behavior of the air. Microscopic dents create a turbulent layer that sticks to the surface of the ball longer than a clean, smooth stream. Due to this, the airflow flows around the ball more efficiently, reducing the area of turbulence from behind. The resistance decreases, and the ball flies further. In fact, dimples increase flight range by tens of % compared to a smooth ball. In addition to reducing drag, dimples affect lift. When the ball rotates, the Magnus effect is created. The air moves around the ball and creates a pressure difference from above and below, causing the ball to rise slightly. The right combination of rotation and dimples allows the player to control the trajectory, make high punches, sharp turns, or precise landings. In this way, dimples become a control tool, not just a decoration. Modern bowls usually have from 300 to 500 dimples. Their size, shape, and location are carefully designed by engineers. The circular recesses create a uniform aerodynamic behavior, but some manufacturers are experimenting with different geometries in an attempt to improve flight. Even a small change in the dimple position can affect the stability and range of the impact. Professionals choose the ball based on how it reacts to rotation and impact force. Interestingly, dimples do not directly affect the feeling of impact or control in the hands. These characteristics depend on the stiffness of the core and shell of the ball. But without them, any strike would be unpredictable, especially over long distances. With the help of dimples, players can predict where the ball will fall and create strategic combinations on the field. The history of dimples is an example of how observing nature and experimentation have led to technological improvement. People noticed a random improvement, studied it, and turned it into a standard. Today, almost all sports balls use similar principles. Golf clubs, rugby balls, and even tennis balls take aerodynamics into account to a certain extent. Dimples are small depressions with a big task. They reduce drag, create lift, and make the ball's flight stable and predictable. Thanks to them, golf has become not just a game of strength, but a game of technique, precision, and strategy. Each indentation on the ball is a bridge between physics, engineering, and the skill of the player, which turns hitting into art and the flight of the ball into a perfectly calculated trajectory. The dimple ball is an example of how a seemingly inconspicuous detail can completely change the result and open up opportunities that would otherwise be unattainable. How is wine made? Wine is a drink that humanity has been creating for thousands of years, turning simple grape juice into a complex and multifaceted product. Its production is a combination of nature, chemistry, and art, where each stage affects the taste, aroma, and color of the final drink. Despite its apparent simplicity, the process requires patience, observation, and an understanding of the biological processes occurring in grapes and wort. The basis of wine is always grapes. The varieties, climate, and soil determine the future taste of the drink. White and red varieties differ in the content of pigments and acids, which affects the color and structure of the wine. Grapes are harvested manually or mechanically, trying not to damage the berries in order to preserve the juice and flavor. Harvesting usually occurs when the sugar in the berries reaches an optimal level, which is important for proper fermentation. The next stage is grinding and pressing. For white wines, the berries are crushed and the juice is squeezed out, and the skin is most often separated so that the drink remains transparent. For red wines, the juice stays with the skin, as it contains pigments and tannins that give color and texture. Sometimes, a small amount of sulfur dioxide is added to prevent premature oxidation and unwanted bacteria. Next comes the fermentation stage, which turns the sweet grape juice into alcohol. Yeast is added to the juice,
microorganisms that feed on sugar and release alcohol and carbon dioxide. Natural yeast can be found on the surface of the berries, but many winemakers use specially cultivated strains for a more predictable result. Fermentation lasts from several days to several weeks, depending on the temperature, grape variety, and wine style. During this process, sugar gradually disappears, turning into alcohol, and dozens of aromatic compounds are formed that create a wealth of flavor. After fermentation comes settling and aging. The wine is left on the lees, yeast residues, so that it becomes cleaner and acquires complex flavor notes. Some wines are aged in steel tanks, others in oak barrels. Oak gives the drink vanilla, woody and spicy notes, and also softens the acidity. Exposure can last from several months to several years. During this period, the wine matures. Its taste profile becomes more harmonious. The aroma is saturated, and the structure is dense and rounded. After aging, the wine is filtered to remove yeast residues and particles, and bottled. Sometimes a small amount of sulfur dioxide is added to stabilize and preserve the taste. Red wines can be blended, a mixture of several varieties to achieve a certain balance, or single grape, when a single grape variety is used. White and rosé wines can also be mixed, or aged with minimal intervention, to preserve freshness and fruity notes. Wine is not only a chemical reaction of sugar and yeast, but also the result of subtle biological and physical processes. Yeast creates esters and aldehydes, which impart fruity and floral notes. Tannins from the skin and seeds regulate the astringency and texture, while acids make the taste lively and refreshing. Even the storage temperature affects the taste. Wine that is too cold or too warm loses its flavor and balance. The history of wine is a story of patience. Humanity has been observing nature for centuries, experimenting with grape varieties and fermentation methods. Each region of the world has developed its own traditions. French, Italian, and Spanish wines differ in style and technique of production, reflecting the local climate, soil, and culture. Wine is a product that combines biology, chemistry, and culture. It starts with sunny berries, goes through the processes of fermentation, aging, and blending, and turns into a drink that can tell the story of the place, time, and people who created it. Wine reminds us that nature and human labor together create something more than a simple liquid. It becomes a cultural and emotional experience that unites generations and traditions. What is fermentation? Fermentation is one of the oldest and most amazing processes that humanity uses to transform food, beverages, and other substances. In fact, fermentation is a biochemical reaction in which microorganisms, such as yeast or bacteria, decompose organic substances, most often sugars, into simpler compounds, releasing energy and creating new substances. This process underlies the production of bread, wine, beer, kefir, yogurt, cheeses, sauerkraut, and many other products, and is also used in industry to produce alcohols, acids, and medicines. First, Let's look at the biological basis. Each grain, fruit, or vegetable pulp contains sugars and other carbohydrates. Microorganisms such as yeast or lactic acid bacteria have enzymes called proteins that accelerate chemical reactions. When a microorganism encounters a suitable environment, enzymes break down sugar into simpler compounds, most often alcohol and carbon dioxide, or lactic acid in the case of lactic acid fermentation. The process releases energy that the microorganisms use for growth and reproduction. There are several types of fermentation. The most famous is alcoholic fermentation, used to make wine and beer. Yeast converts sugar into ethyl alcohol and carbon dioxide. Carbon dioxide creates bubbles in champagne or beer foam, and alcohol makes the drink strong. Alcoholic fermentation can take place at different temperatures, which affects the reaction rate and taste characteristics of the product. For example, warm fermentation of beer gives more fruity aromas, while cold fermentation gives a cleaner taste. Another type is lactic acid fermentation. It is typical for yogurt, kefir, cheese, and sauerkraut. In this case, lactic acid bacteria convert sugar into lactic acid. The acid creates an acidic environment that prevents the proliferation of harmful microorganisms and gives the products their characteristic taste. Lactic acid fermentation also improves the digestibility of food. Proteins become softer, and vitamins and trace elements become more accessible to the body. Fermentation is not limited to food. In industry, it is used to produce ethanol, acetic acid, antibiotics, vitamins, and biofuels. In laboratories and biotechnological industries, specially grown microorganisms ferment substrates, creating the necessary chemical compounds. This process is called industrial or controlled fermentation. The history of the use of fermentation dates back to ancient times. Archaeological finds show that people were already making alcoholic beverages from fruits and grains 7,000 years ago. Sauerkraut, kimchi, and yogurt were known millennia ago, although people did not understand the biochemistry of the process. They simply observed that certain conditions created delicious and durable foods, and passed on knowledge from generation to generation. Fermentation has been studied scientifically since the 19th century. Louis Pasteur proved that living microorganisms are responsible for this process, and not spontaneous generation, as previously thought. His discoveries became the foundation of microbiology and the modern food industry. Fermentation also has a social significance. It allowed people to store food, create drinks, and unite communities around the kitchen and feast. Many traditional dishes from different cultures are the result of long-term observation of fermentation. From wine and beer in Europe to miso and natto in Japan, from kvass and fermented baked milk in Russia to cheeses and yogurts in the Mediterranean, fermentation has become part of the civilizational memory of mankind. What is made from oil? Oil is one of the most versatile natural resources, and it produces a huge number of products that surround us in everyday life. Although most people think of oil primarily as a fuel for cars, its applications are actually much broader. It becomes a raw material for fuels, plastics, chemicals, cosmetics, medicines, and even food. Understanding how oil is transformed into these materials reveals the amazing chemical and technological complexity of the process. Oil itself is a mixture of hydrocarbons, organic compounds consisting of carbon and hydrogen atoms. It was formed millions of years ago from the remains of plants and animals, which, under the influence of pressure and temperature, turned into a viscous liquid. Oil is extracted from the ground through wells and transported for processing to refineries. There, it is divided into fractions by a process called distillation. Distillation is the heating of oil, in which different components evaporate at different temperatures and then condense separately. This is how gas, gasoline, kerosene, diesel fuel, fuel oil, and petroleum oils are produced. Gasoline and diesel are perhaps the most famous refined products. They serve as fuel for cars, trucks, planes, and ships. Kerosene is used not only in aviation, but also as a household fuel for heaters and lamps. The gas released from the oil goes to industry and homes for cooking and heating. But oil is valuable not only as an energy source. The chemical industry uses oil as a raw material for the synthesis of materials. Plastics, polymers that have become an integral part of modern life, are made from petroleum fractions. Polyethylene, polypropylene, polyvinyl chloride, and other types of plastic are obtained by processing hydrocarbons. These materials are used in packaging, construction, electronics, medicine, and clothing. Even everyday items such as plastic bottles, toys, containers, and pipelines are products of refined petroleum. Oil is also used for the production of synthetic fibers. For example, polyester and nylon are materials for clothing, carpets, fabrics, and technical products. They are created from monomers that are obtained from petroleum hydrocarbons. These fibers are durable, wear-resistant, and flexible, which makes them in demand in industry and everyday life. Other refined products include lubricating oils, bitumen, and asphalt. Lubricating oils are essential for the operation of engines and mechanisms, reducing friction and wear. Bitumen is used in the construction of roads and roofing materials. The asphalt that covers the streets is also a product of oil refining and ensures the durability and strength of the coatings. Oil is also used in pharmaceuticals and cosmetics. Mineral oils, petroleum jelly, lotions, and creams contain substances derived from petroleum. In medicine, petroleum products are used to make tablets, capsules, and various medical products where they serve as the base or stabilizer of active substances. Even in the food industry, oil leaves its mark. For example, food additives, packaging, and some food flavors are produced using petrochemicals. Although oil is not directly included in food, it provides storage and transportation, allowing products to stay fresh and safe. Modern petrochemistry is a complex combination of science and technology. Crude oil is a raw material that is transformed into tens of thousands of different substances in the hands of engineers. Each stage of processing requires precise control of temperature, pressure, chemical reactions, and separation of components. This is how a simple, natural liquid becomes the basis for energy, industry, medicine, and everyday human life.
Do horses need to produce glue? Many people imagine glue as a modern, synthetic product. But historically, glue was a natural substance obtained from animals, most often from horses and cows. Horses were indeed used to produce glue, but today their role has been almost completely replaced by industrial methods. To understand why horses were needed, you need to consider what glue is, what it consists of, and how it was produced before. Glue is a substance capable of joining materials, turning them into a single whole. Its properties depend on the proteins that make up the feedstock. Previously, animal connective tissues, such as tendons, ligaments, cartilage, and bones, were used to produce glue. The proteins contained in these tissues, mainly collagen, turn into gelatin when heated and processed, which is the basis of the glue. Collagen has a unique ability to transform from a strong but solid structure into a viscous, sticky mass when heated with water. Horses were valuable precisely because of their large tendons and ligaments, rich in collagen. After slaughtering the animal, the parts suitable for the production of glue were cleaned of fat and meat residues. Then they were crushed and boiled in water for a long time. When heated, the proteins broke down into simpler chains, turning into a viscous liquid. After cooling, this liquid solidified, turning into a solid which was then crushed and sold as slabs or powder. This glue was used in furniture manufacturing, carpentry, book studies, tool repair, and even in art objects where reliable bonding of wooden and leather parts was required. The production of glue from horses had its own peculiarities and limitations. The process was laborious. It was necessary to thoroughly clean the raw materials, cook them for a long time, and control the temperature and density of the resulting product. The glue was natural, biodegradable, and safe, but had limitations in strength and water resistance. For example, such glue easily dissolved in water, which made it unsuitable for outdoor structures or wet conditions. Over time, people found alternatives. First, they started using glue from cow and pig tissues, and later, synthetic analogs appeared. PVA, epoxy, and polyurethane adhesives provided greater strength, water resistance, and durability. Modern industry has almost completely abandoned horse components, although some handicraft or historical reconstructions still use natural glue to preserve the authenticity of the technology. For example, restorers of antique furniture or musical instruments can use collagen glue, identical to the historical one. Interestingly, the use of animals to produce glue has left a mark on the language. Expressions like sticky bonds or sticky situation partly reflect observations of the properties of natural collagen glue. It connects everything firmly, but requires caution when applying. Today, horses are not mated to produce glue. Most of the adhesive products are created synthetically, which reduces costs, simplifies storage, and ensures stable properties. However, the historical role of horses was significant. Without their fabrics, humanity would not have had effective and affordable glue before the advent of the chemical industry. Natural glue from horse tendons is an example of how humans have used living resources to solve technological problems based on observation, experience, and biochemistry of animal tissues. Thus, Horses were an important source of collagen needed to make natural glue, but modern chemistry and synthetic materials have almost completely replaced them in this role. The history of glue shows how humanity is gradually moving from natural resources to industrial technologies, preserving knowledge about natural materials for handicrafts, restoration, and cultural heritage.
This is an example of how the biological properties of animals were used to create practical tools, and then replaced by more universal and safer methods. How is the distance to the stars measured? Distances to stars are one of the most fundamental tasks of astronomy, because understanding distances allows scientists to build models of the universe, determine the size of galaxies, the age of stars, and even search for exoplanets. Despite the apparent simplicity of the question, how far away is the star? Measurement methods are based on a complex combination of geometry, physics, and observational astronomy. The most direct and simplest method is called parallax. Parallax is the apparent displacement of an object's position against the background of more distant objects when the observer changes his position. In astronomy, this means that an astronomer photographs a star from Earth at different times of the year when the planet is at opposite points in its orbit around the Sun. The difference in the position of a star against the background of distant stars makes it possible to calculate its distance using simple trigonometry. The closer the star is, the greater its parallax. The further away, the smaller the displacement. This method works for the nearest stars at a distance of up to several hundred light-years. Parallax is a kind of astronomical ruler created by nature itself. For more distant stars, the parallax becomes too small to measure. Light methods and standard candles are used here. One of these candles is the Cepheids. Cepheids are a special type of variable stars in which there is a strict relationship between the period of brightness fluctuations and the true luminosity. By measuring the oscillation period, the astronomer determines how much energy the star is actually emitting. By comparing this with how much light reaches the Earth, you can calculate the distance. This method allows you to measure distances up to millions of light-years, and even determine the scale of local galaxies. For even more distant objects, cosmological methods based on redshift are used. The light from distant galaxies is being stretched due to the expansion of the universe. The farther away an object is, the stronger the shift of its spectrum to the red part of the spectrum. By measuring this shift and knowing the rate of expansion of the universe, astronomers can determine how far away a galaxy or quasar is. This method is used for billions of light-years and helps to build a large-scale map of the universe. There are also methods based on standard candles of the second level. For example, type 1a supernovae. They have almost the same maximum luminosity, so by measuring the brightness on Earth, you can find out the distance to the galaxy in which the flare occurred. These methods allowed us to determine that the universe is expanding rapidly, and opened a new chapter in cosmology related to dark energy. Astronomers also use triplet methods and spectroscopic parallaxes. When the properties of a star, such as color and spectrum, allow us to estimate its luminosity and, comparing it with the observed brightness, calculate the distance. This method is especially useful for stars for which it is difficult to measure parallax directly. The role of technology cannot be underestimated. Modern space telescopes, such as Hipparcos and Gaia, measure parallax with an accuracy of microangular seconds, which makes it possible to determine distances to millions of nearby stars. With the help of these data, astronomers build accurate three-dimensional maps of the local space environment, observe the movement of stars, their speed and interactions. Measuring distances to stars is not only a matter of geometry and physics, but also a window into understanding the universe. Thanks to these methods, scientists can determine the size of galaxies, the mass of star clusters, the age of objects, and even build models of the evolution of the cosmos. Each method complements the other. Parallax is accurate for nearby stars. Cepheids and supernovae allow you to measure a greater distance, and redshift covers billions of scales. How are raisins made from grapes? Raisins are dried grapes that humanity has been using for thousands of years. Its production seems simple. We dry the berries and get a sweet dried fruit. But in fact, the process requires knowledge of chemistry, biology, and the right technology to preserve the taste, aroma, color, and nutrients. The transformation of juicy grapes into raisins is not just the removal of water, but a complex transformation of the product. The main difference between grapes and raisins is the moisture content. In fresh grapes, about 70 to 80% of the weight is water. In order for the raisins not to spoil, the water from the berries must be removed to a level of about 15 to 20%. It is the reduction of humidity that prevents the development of mold and microorganisms, preserving the product for a long time. At the same time, it is important to preserve the integrity of the peel and the structure of the berry so that the taste remains saturated and the raisins are soft and juicy, not hard and over-dried. There are several ways to get raisins. Natural sun is the most ancient method. Grapes are laid out in the sun or on special pallets, sometimes on special nets, so that the air circulates freely. The sun's rays gradually evaporate moisture, and the peel protects the inner flesh. This method is effective in hot and dry regions, for example, in the Mediterranean countries, Turkey, Iran, or California. The solar method gives raisins their characteristic dark color and rich flavor, but it takes several weeks and depends on the weather. Modern technologies make it possible to dry grapes faster and more controllably. Shade or artificial drying is a process in which berries are placed in drying chambers with controlled temperature and humidity. Here, the air moves forcibly, accelerating the evaporation of moisture. This method allows you to preserve the light color of the grapes, reduce the risk of mold infection, and control the texture of the raisins. On an industrial scale, hot air drying is used at a temperature of 50 to 70 degrees, sometimes in combination with vacuum drying, to preserve vitamins and antioxidants. Some varieties of raisins are processed before drying. Grapes can be treated with alkali or sulfur dioxide solutions to remove natural wax deposits and accelerate moisture loss. This allows you to get a more even color and prevent oxidation, which makes the berries brown. For example, Golden raisins are often treated with sulfur dioxide before drying to preserve their light shade. The chemistry of the process is interesting. During drying, sugars, acids, and aromatic substances are concentrated. Sugar does not disappear, but is distributed throughout the berry, making the raisins sweet and rich. At the same time, partial caramelization of some compounds occurs, which gives a characteristic taste and aroma. Antioxidants such as polyphenols remain in the skin of grapes, which are preserved and enhanced in dried berries. The quality of the raisins depends not only on the drying method, but also on the grape variety. Different varieties produce raisins of different colors, sizes, and flavors. Small varieties, such as Corinca, produce a mild, sweet product with a rich flavor, while large varieties produce dense, harder raisins. In addition, the climate and storage conditions affect the durability of the product. Humidity above 20% can lead to mold, and too dry raisins lose their softness. Raisins are used in cooking, confectionery, as a snack and an addition to baking. It is rich in sugars, B vitamins, potassium, and antioxidants, which makes it a valuable, nutritious product. Interestingly, in some cultures, raisins are used not only as food, but also for medicinal purposes, considering it useful for digestion and the heart. What is skin? Skin is a unique biological material that mankind has been using since ancient times. In nature, it performs a protective function by covering the body of animals, and when processed, it becomes a durable and flexible material for clothing, shoes, bags, furniture, and many other products. Understanding what leather is, how it works, and how it is processed reveals the combination of biology, chemistry, and craftsmanship that makes it such a valuable resource. In a living organism, the skin is a complex organ consisting of several layers. Calf skin, bovine, pig skin, and sheep skin are the most valuable among animals, although other types are also used. The main components of the skin are collagen and elastin, protein fibers that give strength, flexibility, and elasticity. Collagen forms a dense mesh that holds its shape and resists tearing, while elastin allows the skin to stretch and return to its original position. In addition to proteins, the skin contains fats, water, and minerals, which also affect its properties. In order for the skin to become suitable for use in production, it must be processed, a process called dressing. First, the skin is cleaned of meat, fat, and hair residues. This is done mechanically or chemically. This is followed by an important step, salting or drying to prevent rotting and preserve the material until further processing. Without this stage, the skin deteriorates quickly, as organic substances become a medium for bacteria. The main purpose of dressing is to turn untreated raw leather into a durable material. One of the traditional methods is chrome plating, when the skin is treated with solutions of chromium salts. This method makes the skin soft, supple, and resistant to water and microbes. There are also herbal methods, such as oak bark tannification, in which tannins from the bark bind to skin proteins. This method gives a tougher but durable leather, which is used for shoes, belts, and furniture. Vegetable tannins also give the skin its characteristic color and fragrance. After dressing, the skin is dried, stretched, and polished. These processes make the material smooth, flexible, and ready for painting. The skin can then be stained, protective coatings applied, or textured to enhance its appearance and properties. Different processing methods produce different types of leather: smooth, lacquered, suede, grainy. Each variety has its own unique properties, suitable for certain products. Leather is valued for its combination of strength and flexibility. It is tear-resistant, durable, and pleasant to the touch. In addition, the skin breathes. It allows air to pass through the pores, which makes the products comfortable to wear. This is especially important for clothes and shoes. Leather furniture and accessories also retain their shape and last for decades with proper care. Historically, leather was one of the first materials that people used to protect themselves from the cold and create household items. She made it possible to create clothes, shoes, bags, tents, and even ships. Over time, processing technologies improved. New methods of coloring, tanning, and finishing appeared, which made the leather not only functional, but also aesthetically attractive. In the modern world, leather remains a symbol of quality, style, and durability. Leather is an amazing example of how a natural material can be transformed into a product that meets the high demands of people. It combines the biological properties of a living organism and human skill in processing and improvement. From raw hides to soft, colored, and wear-resistant leather, this path requires knowledge of chemistry, physics, and handicrafts. This is what makes leather a unique material that has been used for centuries in everyday life, art, and industry.